clock?
There's no clock.
I'll try to.
That's
the time.
right.
Yeah, no, just tell me when I'm running out of time. Okay. All right, thank you. So, first of all, thank you to the organizers for the opportunity to speak in this very interesting workshop and for all the hard work organizing it. The title of my talk is the Swampland, Duality, and De Sitter Entropy. And this is work to appear with Gary Shu, Hiroshi Oguri, and Kunwon Waffer. So, many string theory settings satisfy a relation of this form, where derivative of the potential goes like the potential with some constants of order 1. And we've already seen to talk about it, and I think we'll probably hear more about it later on in the conference. And it was suggested that this might even be a Swampland criterion, the so-called De Sitter conjecture. Like a generic problem in some sense that we all face when we think about the Swampland is the question of if we see something happening in many examples, is this just a property of those examples, or is this a more general argument why you would expect such behavior to occur? And the work that we are doing, that I will talk about, is basically trying to give this more general argument as to why we might expect this kind of behavior more generally. So the starting point actually is a different Swampland conjecture, the so-called Swampland distance conjecture. And for supersymmetric settings, at least with 8 supercharges, this can be stated very sharply. So approaching any infinite distance locus in moduli space, there is an infinite tower of states which becomes exponentially light. And we just heard a really nice talk about this from Eran. And as I said, for at least 8 supercharges, I think it's one of the most supported of the Swampland conjectures. And it can even be proven in very, very general settings. So I think it has a lot of support, and we'll probably hear more talks about it. And it also was mentioned, it can actually be tied again to the weak gravity conjecture. In some sense, it's related to a kind of weak gravity conjecture for scalar fields. So I think it's a well-motivated conjecture. And there's also a kind of stronger version of this conjecture, which says that the exponential behavior appears already at Planck scale displacements, and the exponent is order 1. And this was kind of implicit already in the original papers. But more importantly, it tells you that it should hold also for fields with a potential. And that's a highly non-trivial statement, because it tells you that it's not just a statement about field spaces, but it's a statement about the kind of potentials you can get in string theory. So this was conjectured to be the case. And again, this has passed some non-trivial tests, but I think it's less tested than the moduli space one, so fields with potentials. And it's fair to say there are still many open questions about it, but yet still it has passed a lot of tests. So in this talk, I will assume its validity. So I will assume that the conjecture holds even for fields with a potential. And I want to go back a little bit and to try and understand what was the underlying motivation for even proposing the conjecture in the first place, and why we might expect that this could be actually general. And I think the underlying motivation is duality, duality that we find in string theory. And the idea is that somehow when you go to large distances in moduli spaces, then you see new light states appearing, and those light states will form some dual description of the physics for you. That's the idea. So moduli spaces in string theory look something like this. There is some bulk. And then when you go out, there is some light states that become light, and then there is some description in terms of these states which offer some dual description of your theory. Perhaps the most famous picture of this is actually the M-theory circle. Again, all of these points are regimes where we have some description of the physics, and they are all at infinite distance. So, but the idea is that somehow it's more general, and this is the underlying idea behind this behavior. And in string theory, all couplings are scalar fields. So whenever you go to some kind of regime where you try to have some well-controlled effective theory, at least parametrically well-controlled effective theory, then you're ending up going to large distances in field space. That's always the case. That's what it means. Quite often it's also the other way around. Large distances imply weak couplings, but that's a little bit less general maybe. There might be ways to kind of get around that. But certainly this way is nearly always true. Weakly coupled regimes are far away from the bulk of the moduli space. So let me give some examples of this in 4 dimensions, let's say. So for example, think of type 2b on a Calabi-Yau. And I think in some sense the first example of this idea was the conifold, where we have some singularity that we see in the moduli space or in the space-time. We can see this from perturbative string theory. On the other hand, a D3 brane becomes light, and we can recover this singularity by instead thinking about the D3 brane and just integrating it out. So that's a dual picture of the physics, and it gives you a much simpler answer, a much simpler way to arrive at that physics. And there are many examples of such things. Let me mention one of them, which is it's actually a mirror setting, not 2b in Calabi-Yau, but in 2a. Again, you can find all kinds of geometric invariants, and you can understand it in terms of loops of D-brane states, in this case D0, D2, D0 bound states. And the most relevant example for this talk is the one we just heard about. If you go to infinite distances in moduli space, then a lot of the physics, the geometry on the moduli space, the gauge couplings of gauge fields, all of this physics can be gotten, but now not from integrating out a single number of states, but integrating out a whole infinite tower of D3 branes. So these are all pieces of evidence towards the fact that when you go to large distances in field space, there is a tower of states, and this tower of states offers you a dual description of the physics. So you can calculate things by working instead with a tower of states. So we will interpret the Swampland distance conjecture in this way, that any weakly coupled region in string theory should have a dual description in terms of a tower of light states. That's the underlying physics. And now what we do is we say, well, this dual description doesn't just give you things like gauge couplings and moduli spaces, geometries, but it also gives you the potential. Why not? If it's a dual description, it should give you the full theory. So we will apply this to the potential. So that's not so crazy. One piece of hand-waving motivation you can see for this, in n equals 2, for example, the only way you can write down a potential is by gauging an isometry in field space. So that means that the existence of a potential is intrinsically tied to the gauge couplings. So for example, if you gauge some of these fields, then the way that you gauge them with the gauge couplings here, or the killing vectors, is precisely the thing that gives you the potential. So if the gauge fields and the gauge couplings are emergent from this tower of states, then so must the potential be. It's the same information in n equals 2. And in fact, this n equals 2 structure also underlines pretty much all the potentials that we study in string theory. There are truncations of this. So if gauge fields are emergent, so should the potential be. So how can we make a general connection between this tower of states and the potential? So we don't know how to do that. That would be complicated and very interesting thing to do, and certainly I think it's worth doing in future work. We don't know how to do that generally, and we're after some general result here. But the point is that in de Sitter space, we'll be able to use a trick to give a general connection like this, and that's what we want to do. So let's think about de Sitter space. De Sitter space has a finite horizon for an observer of some radius r, the radius of de Sitter space. And because you have an horizon, you expect to associate an entropy to this. And this entropy, you'd expect to be some log of some dimension of some Hilbert space. And this should be like the area of the horizon, so like r squared. So we will consider de Sitter vacua in our setting, but we'll also allow for quasi-de Sitter vacua. So things that are slowly rolling, like inflation or our current universe that's accelerating, some quasi-de Sitter vacua. So something which has some behavior like this, where alpha is smaller than 1, or of order 1, or much smaller, not as order 1, a little bit smaller, or much smaller. And now the idea is that if you're in some kind of quasi-de Sitter regime, you have some notion of a horizon, and some notion of entropy, and this entropy goes like the inverse Hubble scale squared. If it's a cosmological constant, that's precisely the radius of de Sitter space squared. But that's just also nothing but the value of the potential, the inverse value of the potential. So in any such kind of quasi-de Sitter regime, there is a connection between the entropy and the potential. So that's the first thing we will use. And we should note that we cannot really say too much away from these regimes. So if in some very fast-rolling regime, or not in any kind of quasi-de Sitter regime, there is no well-defined notion of entropy then, and we will not be able to say very much away from them. But note that if you're already in some fast-rolling regime, then already alpha is much bigger than 1, and then you're kind of already satisfying the conjecture. So the things that we'll have to say are the ones that are most relevant in terms of understanding the conjecture. So that was one thing, entropy of de Sitter space. Here's another thing. On the other hand, the distance conjecture says that when you go to large distances in field space, you get many light states. So let's introduce some notation. So we get a tower of light states with some associated mass scale m, and we'll say that there are n tilde such light states below in Planck, and n such light states below some effective cutoff scale that I'll talk about in a second. And because the fields are becoming exponentially light, the number of these states below any fixed cutoff scale is exponentially increasing. So in particular, n goes like some exponential, grows exponentially with the field that you're going, with some order 1 coefficient. So that's what we will utilize. And because you get now many new light states in your theory, well, that's lots of new degrees of freedom, so that means you have a lot of entropy associated to those. So there's an entropy associated to this tower of light states. And this entropy will be some function of n, the number of light states, obviously, and also possibly the radius of the de Sitter space, or quasi-de Sitter space that you're looking at. So there is an entropy associated to this tower, and then the cutoff scale is defined as a scale above which the states no longer contribute significantly to the entropy. So that means we're only interested in states in the tower that are going to give us some contribution to the entropy, so they're going to appear in this expression for the entropy of the tower. Now, since n and r are much bigger than 1, then you'd expect this function here to be dominated by some term. So n and r are huge numbers. So we can parameterize it in terms of some behavior like this, n and r to some powers p and q. These are unknown powers. We will have a go at calculating them later, but for now they're just parameterizations of the entropy of the tower. And now we go back to this duality proposal. The duality tells us that the tower of states should offer a dual description of the potential. And if that's true, then the entropies should match. So we should set them equal to each other. So the entropy of the tower should be the entropy associated to the potential. That's the entropy of the de Sitter space. So we set them equal to each other. And now we can just solve for r in this equation and put it back into the expression for the potential, which is 1 over r squared. And we will get the behavior of the potential. So we solve for r. The potential goes like 1 over r squared. So the potential goes like this behavior in the number of light field. And now we can take a derivative of this. What is that? That's just the variation of the potential with the number of light fields times the variation of the fields with respect to phi. But we know what this is. That's what the distance conjecture tells us. That's exponential. So that's just going to give us some constant b times the potential itself. And we know what dv by dn is because that was the expression for the entropy that we had. You just take this dv by dn you just get from this. And so what you get is something like the de Sitter conjecture. And the constant now is just given in terms of these order 1 numbers. So b is the exponent in the distance conjecture, and p and q are these parameters that parameterize how the entropy in the tower depends on n and r. So we recover this way the de Sitter conjecture. And the physics behind it is actually not so hard to understand. It's quite simple in many ways. You go to some weakly coupled regime in string theory. There is some tower of light states that become light. The coupling is a field. And the entropy is going to increase the more states become light. So what's that field going to want to do? It's going to want to increase the entropy, so it's just going to want to keep rolling. So that's precisely what's being captured by this physics. And in many ways, it's a generalization of an old argument due to Dine and Seiberg, that at weak coupling you expect kind of runaway behavior. But now it's a much more general statement that we're making for any kind of fields and any kind of couplings. But we, of course, utilize the idea that we're in some kind of quasi-de Sitter regime. So that's the cost, but we make a much more general statement. And there's something to note, actually, that even if the tower only accounts for some fraction of the total entropy, so if you add some constant to the whole entropy that's coming from something else that doesn't depend on the field phi, you would not get C order 1, but you will still get that this derivative has to be non-zero, because of the physics I just said. The scalar is always going to want to increase the entropy, so it's always going to want to just keep rolling. There's nothing asking it to stop rolling. So let's just summarize what I just said. We made 3 assumptions: that the Swampland distance conjecture holds for potentials, that we're in a weakly coupled regime where there's the tower of states, and this tower of states is the dual description of the physics, and that we're in a quasi-de Sitter setting, so some kind of accelerated expansion with a nice horizon, where we can assign associated entropy to this setting. And with those 3 assumptions, we recover the de Sitter conjecture. Okay, so P and Q are these numbers that parameterize how the entropy of the tower depends on N and R. And in fact, getting a de Sitter conjecture is not sensitive to the values of P and Q. If there are any order 1 numbers, you get C as order 1. So that's quite nice, because counting the entropy associated with the tower is a hard problem. But the important point to note is that to get a de Sitter conjecture is not sensitive to what that counting is. But the cosmology and the phenomenology is very sensitive to that counting. So that's why it's worth giving it a go, and we gave it a go. So as I said, to know how the entropy of the tower behaves, you need to count the microstates associated with that tower. So that's a hard problem. You need to count the microstates in the dual theory with those states. And by duality, this would essentially amount to counting microstates of de Sitter space. So that's not an easy problem, but and I think it's fair to say that we are not sure that we did it correctly, so we parameterize it generally. But as I said, the de Sitter conjecture is not sensitive to how you count things. We did give it a go, so this is what we said. Consider de Sitter space. There's 3 types of states in de Sitter space. There are so-called quantum field theory states that are localized within the bulk of de Sitter space. There are black holes in de Sitter space, and there are states that are localized on the horizon of de Sitter space. And one proposal, which is the one we looked at, for counting the microstates, is to consider all the localized quantum field theory states in the bulk of the de Sitter space. So we count states that are in some box of finite size R. So consider one relativistic particle in a box of size R. How do we count its microstates? Let's calculate the entropy associated to it by just counting momentum modes of that particle. These are all states, so we just count how many momentum modes we can have. Well, then the entropy goes like the maximum momentum, so up to some maximum value of the momentum of the field, like the maximum momentum of the field times R, which is 1 over the minimum momentum, since it's in the box, cubed. That's just counting all the different momentum modes you can have in that box. Now, the maximum energy associated with these modes is then just going to be this times the momentum scale, k max. And now comes the important point. We're only going to count what we call localized quantum field theory states. That means that these states that are not strongly gravitationally interacting. So we're not allowed to form black holes anymore. So that means that we have to require that the Schwarzschild radius of this energy scale should be less than the size of the box, so that we're not forming any black holes. So that puts a limit on how much momentum we can put in these states. If we put too much momentum in, we're just going to get a black hole, and we don't want to count those. So that tells you that the maximum momentum is actually less than R to minus a half, and so the entropy is less than R to the 3/2. And actually, this is a very old result. It goes back to the 80s, and it tells you that the entropy associated to some non-gravitational fields in a box at most scales like R to the 3/2. So that means that we're never going to be able to recover the de Sitter entropy from these kind of particle, because that scales like R squared, and this scales like R to the 3/2. But that's just one particle. What if you have many particles? That's the situation we're in. So we have to consider situations where we have n such species of particles. We need these to be relativistic to contribute significantly to the entropy, so that means that this effective cutoff below which we count the number of states is essentially the maximum momentum scale. And it's a very simple argument to deduce the number of species you need in order to recover the de Sitter entropy from this dual description. So to maximize entropy, you want to set so the way to do it is you could make a thermodynamic argument and associate a temperature to each species. And in order to maximize the entropy, you want to distribute this temperature equally between all the different species. And now the entropy just goes like TR cubed. So instead of K max, now we have some temperature, if you like. And we have n species, so we multiply it by n. The energy is n times T times TR cubed. And now again, we impose that they should not form black holes. That means there's a maximum temperature we could have within each species. And that tells us there's a maximum entropy that we have. But this then gives us the answer, because that tells us how the entropy of n light states depends on n and on r. That's precisely what we called P and Q before. That's the thing we wanted to calculate. So in order to recreate the de Sitter entropy, since we need n to be r squared, then we get this whole entropy to go like r squared. So we need n go like r squared. The temperature, the maximum temperature goes like 1 over r, so it's a very low temperature. And the entropy associated to each species is then just 1. It's like the minimum entropy you would associate to a field. So it's a kind of a strange thing. It tells you that if you want to recreate de Sitter entropy from non-gravitationally coupled states, then you need to take a huge number of species of order r squared, and you need to assign the minimum entropy to each such species. The fact that it's a low entropy basically means that each species only has one momentum mode excited. So it means that it's not really a thermodynamic limit, but this argument is kind of giving you a limit in behavior. But it's easy to check just by counting microstates that this is the right answer, actually. I won't mention it now, but this is the correct answer, just even if you just count microstates explicitly. So as I said, the de Sitter conjecture is not sensitive to the type of microstate counting that one does. What we did here was just propose a particular microstate counting, and that gave us a P and a Q. P equals a quarter and Q equals 3/2. But for any P and Q, you get the de Sitter conjecture. But the cosmology is very sensitive to the way you assign the entropy to the tower. So to see this, let's say we apply this to our universe. So let's imagine our universe is in some quasi-de Sitter regime, which it is. And let's imagine it's in a weakly coupled regime, and therefore there should be some dual description of it in terms of tower states. How must this tower states look like today? So we have R being 10 to the minus 60 today. In order to be a quasi-de Sitter regime, we need C to be less than 0.6. We assume that this tower states should be equally spaced. That's a very natural assumption. So remember, in order to recreate the de Sitter entropy, we had this relation between n and r. So this tells us how many states we need. I'll consider two types of effective cutoff scales. Either n Planck, so we either count all the states below n Planck, or we count all the states below 1 over square root of n. That's the species scale. That's also a scale that rises very naturally in many settings. So I'll consider two such scenarios. And then the mass scale is just simply the cutoff scale by the number of states, since it's equally spaced. So it behaves like this. So then all I need to do now is just, if I know a P and Q, so if I know a microstate counting scheme that counts the microstates of this tower, then I get a prediction for all of these things. So let me just show some benchmark scenarios to give you some idea what this would imply to. So the first thing is the counting we just did. That's counting microstates by looking at quantum field theory states that are not strongly interacting, so do not form in black holes inside a box. That means that Q is 3/2 and P is a quarter. Well, that gives you that n is 10 to the 120 in our universe, and the effective cutoff scale is 10 to the minus 60. And so if they're equally spaced, the tower, the mass scale is 10 to the minus 180. Everything is in Planck units. So this is very, very light. A lot of states, very, very, very light. It's either, if our universe is in this setting, in this situation, and this is the correct microstate counting scheme, which we don't know if it is, but if that was the case, then you could deduce either two things. Either there's something about the duality we don't fully understand in terms of this tower. Maybe they are there and somehow integrated into the space-time already. Or more likely, that this is just ruled out phenomenologically. We just don't see so many light states in the universe. And so one would deduce that we have to be away from this weakly coupled regime. So we have to be in some strong coupled regime. There's no tower of states that provides a dual description of our universe. And that's what we don't see then. But that depends on this particular counting scheme. Let's look at another counting scheme you might consider. For example, you might consider Q equals 3/2 and P equals 1. That basically tells you that that's actually the same as if you took just one of these species. Then it has a Q to the 3/2 scaling of the entropy. And then you just multiply this by n. That would give you this kind of counting scheme. Then you would need n to be 10 to the 30. The cutoff, the species scale, if you're interested in it, would be around the TeV scale. And the mass of these states would be, if the cutoff scale is the Planck scale, then around the neutrino scale or below it. So that's getting a little bit more phenomenologically realistic. If you do counting, if you apply this kind of counting scheme, you get a huge tower of states around the neutrino mass scale. And well, for Q equals 2, you reach a limiting regime, because that tells you that each field contributes R squared entropy, so then it doesn't really matter how many species you have. So it's not really sensitive to n. The tower can be any kind of property you like. So halfway between these two is Q equals 7/4, and then you find that you need 10 to the 15 species. The species scale is 10 to the minus 7, and the tower state sits somewhere between the MEV and TeV scale. So I repeat, getting the de Sitter conjecture is not sensitive to how you count the microstates of this tower, but the cosmology is very sensitive to how you count the microstates of the tower. We gave a calculation of an example counting scheme, but there could be other ones. We cannot be sure what's the correct one. So to summarize, we proposed that the weakly coupled regions in string theory admit a dual description, and this dual description should include a description of the potential by the tower of light states of the Swampland distance conjecture. We already have a lot of evidence for this, actually, for not the potential, but for things like gauge couplings and the field space metric. We just had a very nice talk about it. In a quasi-de Sitter setting, the duality can be applied to the entropy, and it leads to the Swampland de Sitter conjecture. We have calculated an example approach of counting the microstates associated to this tower, so then we can make this entropy precise, matching precise. And for that approach, we find that our universe would most likely not be in a weakly coupled regime. For other type of microstate counting states reveal a very varied cosmology, and it would be interesting to study the relation between this microscopic physics, the counting of the microstates, and the phenomenological cosmology that you get. That's it. Thank you.
Questions?
I need to do something? Just like that. Let me see if I understand correctly your point of view. The essence of what you are telling us is that the de Sitter entropy, which you call n, changes with time. And you justify that this entropy changes with time using the distance conjecture. In other words, saying that the degrees of freedom that contribute to this entropy behave with phi, with the moduli, in such a way that need to increase or decrease exponentially because of the conjecture, This is the essence of what you are saying?
Yeah, exactly. So you think of rolling away in field space or moving away in field space, you get many of these light states. They have an entropy associated to them, but they also are a dual description of the potential. So you should equate the two entropies, and then this is what you get.
Yeah, that's the argument. The reason de Sitter is quantum mechanical inconsistent that we were just advertising is not only because you identify what is the origin of the variation of the entropy with time. We have some other picture of that, which is simply that whenever you move in time, indirectly you move in moduli space, and when you move in moduli space, the number of light degrees of freedom increases.
Yes.
That's your point.
In a weakly coupled regime where the tower is a dual description, it might be that you're in some strongly coupled regime, and then we don't know how to describe the entropy.
The key point in your computation is derivative n with respect to phi.
Yes.
Okay, we can discuss it.
Yeah, it's what you say, basically. Yeah.
Okay.
Your argument sounds similar in spirit to a paper by Joe Conlon, I think 6 years ago, on why large field inflation is in tension with entropy considerations. But what confuses me is that he never had to use the distance conjecture, and still he got a tension between two ways of calculating entropy, and he concluded that large field inflation is problematic.
Yeah, I mean, the calculation is very different to what we do, and it's a very different argument. So it's not, I mean, at all levels it's different. It didn't count the states of this tower. He didn't count microstates the way we did. He looked at the horizon, and it was a very different argument. But it's true that in spirit, he was trying to do something similar, to say that there is the kind of the trouble that we're finding with very large distances is related to the finiteness of the set of entropy. So in that spirit, it's similar. Yeah.
Maybe it's a detail, but so with your reasoning, you reach a relation between the derivative of a potential and the potential. What about the inequality? So you don't really get an inequality, you get an equality, actually.
Yeah, so that depends on a number of things. We cannot make a very sharp statement, because they're kind of roughly, it depends on the nature of this duality. So for example, it could be that the tower state doesn't account for 100% of the entropy. you probably wouldn't expect that to be true. There could be some other contribution to entropy, and then you would expect some inequality signs or something like this, but we can't make it very precise.
Just to clarify, the number of towers of state is bigger than the end. The number of towers should also be monotonically increasing as we approach the boundary. That gives you an inequality. So equality is if there's only one tower. If you get more and more towers, you get more and more. Any other question?
How C depends on the exponent B.
Sorry?
The C in the inequality in your model, how depends on B?
Yeah. Not only, but as I said, it also depends on how you count the microstates of the tower.
On B, how it depends
on B? Yeah, it depends on B. Yeah.
He wants to show him the formula.
You want to see the formula? Here. So B is the exponent. Yeah.
And B, you have any guess?
So as I said, the refined conjecture says that it should be order 1. B is order 1. And we have all the tests that we know of in string theory tell you that B is order 1. So it's very difficult to make B very, very small, which is what you want to go very large distances. Yeah.
Okay, so we thank Eran. Okay, so for lunch, for those who don't know the campus,